Have you ever wondered how something so massive, made of steel and weighing thousands of tons, can float on water? It seems counterintuitive, doesn't it? This colossal structure, far heavier than any object you might typically see floating, defies our everyday expectations. Why doesn't it just sink like a rock the moment it touches the sea? The secret lies in a simple but powerful concept: buoyancy. This fundamental principle of physics is what allows even the largest vessels to stay afloat, rather than plummeting to the ocean floor. Whenever you place something in water, the water pushes upward against it. This upward push is called the buoyant force. It's a natural reaction from the fluid, constantly working against the downward pull of gravity on any submerged object. If the buoyant force is equal to the object's weight, the object floats. That's why a beach ball pops back up when you push it underwater. The water is literally pushing it back toward the surface with a force equal to or greater than the ball's weight, causing it to resurface. This idea was first discovered over 2,000 years ago by the Greek scientist Archimedes. Legend says he realized it while taking a bath, when he noticed the water level rose as he got in. This seemingly simple observation sparked a profound scientific breakthrough. He understood that the upward force on his body was equal to the weight of the water he displaced. From that discovery came a timeless law, now known as Archimedes Principle, which has guided engineering and physics for centuries. Any object placed in a fluid experiences an upward force equal to the weight of the fluid it displaces. This single principle explains how ships float, how hot air balloons rise into the sky, and even how submarines can precisely control their depth by adjusting their displacement. But here's the puzzle. Steel is much denser than water. Drop a steel ball into the sea and it sinks instantly. So how does a steel ship, made of the same dense material, manage to stay afloat? This is where clever engineering comes into play. The answer is shape and volume. A ship's hull is designed to displace a huge amount of water. Even though the steel walls are heavy, most of the inside is filled with air, which is significantly lighter than water. That air gives the ship a much larger volume and makes its overall density less than that of water. As long as the total weight of the ship and everything inside it is less than the weight of the water it displaces, it will float. This careful balance is crucial for maritime travel. Floating isn't enough. A ship must also stay stable, especially in rough seas. That's where two invisible points matter most: the center of gravity and the center of buoyancy. Their precise relationship determines a ship's ability to remain upright. The center of gravity pulls the ship downward, while the center of buoyancy pushes it upward. Engineers carefully design the hull so these 2 points align in a way that keeps the ship upright, preventing it from capsizing even under challenging conditions. When waves hit, the ship tilts slightly, but the buoyant force shifts to push it back, like nature's balancing act on water. This dynamic interplay ensures that the ship always returns to a stable position, maintaining its course and safety.
The principle of buoyancy isn't limited to ships. Submarines control their depth by taking in or releasing water from special tanks, effectively changing their overall density to either sink or rise through the water column.
Cruise liners weighing more than 200,000 tons float using the same rule as a child's toy boat. Even tiny creatures like water striders use surface tension and displacement to stay afloat, showcasing the universality of this physical law across vastly different scales. No matter the size, from a minuscule insect to a colossal cargo ship, the balance between gravity and buoyancy keeps everything in harmony. When you watch a giant ship glide across the ocean, you're seeing physics in motion, a perfect balance between these fundamental forces. The same ancient principle that Archimedes discovered in his bath now carries people, goods, and dreams across the world's oceans. It's a testament to the enduring power of scientific discovery and its practical applications in our modern world. Ships don't defy gravity, they work with it, turning a simple law of nature into one of humanity's greatest achievements. This understanding has allowed us to conquer the seas, connecting continents and cultures. So now you know why ships float, a marvel of engineering and physics. But here's a question to think about. If a ship can float on water, could something ever float in the air or even in the vacuum of space? The principles might be different, but the underlying concept of balancing forces remains intriguing. Subscribe to Quick Why and join us next time to find out. We'll explore these fascinating questions and delve deeper into the science behind the world around us. Don't miss our next episode.